Hey, Vlad here, devinsidea.com. Welcome to another video. In the previous video, we've seen a pretty compelling use case for continuation passing style. However, our add function, even though it was, or at least seemed to be tail recursive, was still somehow ended up running out of stack. Today, we're going to dig a little bit deeper and try to find out what went wrong. As always, we're in the Ubuntu virtual machine and we're running Sublime Text with a plugin called Terminus, which we introduced a few videos ago. Terminus emulates a regular terminal for us, so we're running SBT, and SBT can run whatever we want for us and even rerun or retest things every time we save the file. So we ended the previous video with having a main method called whyme. So we had whyme. I removed it before I committed. That's why it's not there. So it extends an app. So we had a set of 0, 1, 2, 9, like this, and like that, right? So this was a function that was trying to create a set with 100,000 elements, and we have seen that even though our function seems to be tail recursive, the annotation is silent, the continuation is in the tail position, we still somehow ended up running out of stack, which should happen in just a few seconds. And there we go. Okay, so it seems that the problem is in the line 166, which is, oh, where I was showing remove, but remove looks basically the same. 166, and there's over here. So we're adding the elements in order, and therefore we always ending up in this right case. Now, what does this mean? Is this function tail recursive or not? Because in this line, we have both the continuation and we have both the call to the loop. So which one is it? So what we can do is we can press enter over here so that it's on a different line. And then we can turn the format off, and turn it back on over here, format on, and we can run it again. I'm gonna cut it out from the video so that you don't have to wait for so long. What happened? What jumped? Oh, because it was formatting something, it unfolded something that was collapsed before. That's why it jumped. All right, so this is where we were. No, okay, look at this. I didn't even need to cut it out from the video. Okay, so now it's at line 168. Which means that the problem is actually over here and not in the loop. But in order to be sure, first of all, let's revert that. All right, like that. Let's revert that, and I want to just stop running all the time. We don't need CPS, we don't need stack. We have the Fibonacci. All right, so also had that SH running over there. All right, so let's just do print line high. Okay, so what I want to do is just to be sure that the annotation is not betraying us again. What we're going to do is we're going to rewrite the whole thing with a simple while loop. So I'm just going to copy out the whole thing. I'm going to comment it out. I'm going to copy that. I'm going to paste it over here like this. I'm going to comment it back in. All right. So what we're going to do here is we're not going to use this whole loop. But we're gonna use the match. Are we gonna use the match? No way. You know what? I'm just gonna throw everything out. There we go. Okay, so now we just have the signature. So we had in our loop, we had the set and we had the continuation. So this means that we're gonna have two vars. So this is the var with the set element, which is this. It's coming from here, and we have the continuation, which is a function that takes a set of super, produces a set of super, and it's initialized with identity. So it's basically this line. Okay, so in the end, we're going to call the continuation with, basically it's this case. So I can just comment it out. I actually don't need to do much typing in this case because we're just rearranging things. Okay, so we were looping as long as the set was not empty. So we're going to have as long as set is not empty. Okay. Then what we were doing basically, so it's basically this case, we were deconstructing the set like this, right? So we can take that. I'm not even sure if we need parentheses, but I'm going to use parentheses. So I'm going to do that equals set, right? So it's basically the same pattern match, and now we have this part if input equals empty, right? if this is empty, then we pretty much can jump out of the whole loop and of the whole function. So what we're going to do here is we're going to use the return keyword for the very first time in all of my videos. It's the first time that I'm introducing the return keyword. So what return will do is it will abandon everything and just escape from this entire def, right? So not only from this while loop, but also from this entire def. So we're going to return the same thing that was happening here. Continuation empty, okay? Because remember that this is the case where we're adding an element that already exists, right? And sets cannot have duplicates, therefore there's nothing to do with just returning returning the original set. So we could also return this instead, right? Same as return this, okay? Okay, otherwise it's this case. Otherwise, there we go. We're gonna say, okay, the set is left. That's this one over here. Maybe, you know what, I should copy that. Right. So this is what we had before. So the sat became left, and the continuation became continuation of non-empty. Basically, it's the same thing as over here, like this. And otherwise, oh, by the way, we need, because we have two lines over here, now we need a scope. And the same thing over here. Scala form is going to fix all of this for us then. Okay, and now we can copy that, paste that over here, and we're going to have the right one over here. Now we're almost done. There's a problem though, because you know, this algorithm is what's up? Too many, copied too many. There we go. All right, rearrange everything. All right, there we go. Actually, we can switch to running the test. Actually, before we do that, we need to fix this tiny issue, because every time you write, or you're mixing like this very functional style with something imperative like this was a while loop, you need to be careful what you close over. So over here we sort of had the frozen continuation for free, because this continuation it was closing over this non-empty, and it was also closing, I'm sorry, this continuation, it was closing over this continuation. So what we need to do is over here, let me remove this one. We're gonna do this whole else case. We're gonna put a scope around it. Yeah, the scope. So now over here we're gonna say closed continuation equals continuation, and now over here it's already closed, so we're gonna have it like this, right? So I believe that if I run my test, then everything should still be fine, unless I did a spelling mistake somewhere. All right, everything is still fine, and just as proof, we can also just return this. And in fact, I'm gonna leave it like this. So I'm gonna say same as continuation of what was it before? Continuation of non-empty. All right, continuation of non-empty. All right, there we go. Everything is green. Cool. Now that we have it, let's go back to running YME, which as of right now just prints out hi. Let's switch back to that thing, and if it still explodes, then we know that at least the annotation did not lie to us, that it in fact eliminated the tailcodes, because we were able to manually rewrite it into a loop, and we're still running out of stack. So let's see what's going to happen. And it does at line 190 over here, right? So in fact, this is the problem. Okay, so let me do we still need this? Doesn't really matter. I'm still gonna do print line high, just in case, so that if I accidentally run it again, we don't have to wait for like 10 seconds. All right, I'm gonna switch back to running the tests. There we go. All right, go back to the test. Okay. All right, so again, to repeat, we wrote the whole thing with a regular while loop, and we're still running out of stack. What is actually happening here? What is happening here is that we're building an entire stack of continuations, and then we're calling them all at once, and then we're just running out of stack, right? So there's actually no recursion involved. However, because there's no recursion involved, maybe there should be. So the problem is that the Scala compiler has no idea that it should help us out somehow. So if we made it more explicit that there is some tail recursion happening there, maybe the compiler would actually help us out. Or if it's not capable, then we maybe can write a while loop ourselves. So the idea is to be a bit more explicit over here with what we're doing. So what we want is to produce recipes of the computation instead of doing the actual computation. And then we would stick those recipes into something like a loop or a tail recursive function. And we will manually step through them. And because we can manually step through them, we can, we can write a loop basically that does that. We can do this in constant space. This entire technique that I just described goes by the name of trampolines, or the way that I will be saying them sometimes wrongly, I will be saying trampolines, because somehow I got used to saying trampolines instead of trampolines. All right, so what are trampolines? Trampolines are basically, a trampoline is basically just a loop that is invoking thunk returning functions. Now, it contains a very strange word called thunk, and also thunk returning function. A thunk is nothing fancy. A thunk is a way to write it's a way to delay a computation, but basically it looks like a function with 0 arguments. So you have some expression, you just put it in a function that takes 0 arguments, and then you can later call it. That's all there is. So what we need here is we need to start rewriting our thing in such a way that our continuations are not going to return a set of super, but instead they're going to return a thunk that returns a set of super, right? So basically instead of this, we want to have that, okay? And this is what we're going to do. And by the way, I'm obviously going to leave the link down in the description for trampolines, okay? Trampolines are actually much easier to show than to explain, so we're just going to start doing this. So this is the while loop version. We're going to start with the other one. We're going to jump back and forth between them. So I'm going to have the while loop like this. I'm going to go over here, okay? So what we want to have over here is we don't want this set of super over here. We want the continuation to produce a thunk. Okay, so now we have a thunk returning function. Our continuation is a function that returns a thunk. Okay, so because of this, the entire thing is also going to return a thunk like this. Okay, and because of that, what we need to do is we can do something like this. Trampoline, which is basically a thunk, equals loop. And as default, we're not going to use identity, right? Because identity takes thing, returns it. In this case, it takes this thing and it converts it into a thunk, like this, right? So this is our trampoline, and all we need to do is we need to run it, like this. And this is the whole rewrite. And our test is still green, so it's still doing the same thing. But if I run it, it will still run out of stack. Before we fix that, let's rewrite our while loop version, also to use those thunks. So I'm just going to comment this out, comment this back in, right? So our continuation is now producing a thunk, and this is not an identity anymore. It's something that takes a set and converts it into a thunk, like this. And at the very, very bottom, this is our trampoline, which is a thunk that produces a set of super. And we're just running our trampoline. I believe that everything over here should be fine. Only traits, I forgot an equal sign, okay. Yeah, my years of Scala experience allow me to read only the first few words of an error message. All right, so we've rewritten the while loop like this. And by the way, notice that because we're returning this over here, if we were to return that thing instead, this would be just a trampoline, right? And then we would be forced to run it, right? So there's a reason why I left the this in there, so that it doesn't look so weird. Okay, let me revert that. Okay, so let me revert that back, not revert that back, but like comment this out and comment this back in. The original issue that we had was that even though we had a tail recursive algorithm, we had a bunch of continuations that were always going forward. We're building up the stack, and we simply didn't have enough memory of the stack. So what we have now is we have this separation between the algorithm and the running of the algorithm, right? But we're still gonna run out of stack. I could show this to you, but I don't want to waste like extra 10 seconds. We're still gonna run out of stack. So this is where this cool trampolining technique is coming in. The idea is that this thing sort of looks like a car with an automatic transmission. We already know how to run, and then over here we're just saying run, and then it just runs and builds this entire stack. The idea is to slow it down. The idea is to switch to manual transmission and allow the trampoline to expose a few things on the outside, right? And so our algorithm over here will need to be a bit more explicit about when should we keep going or when not, and then we can write a loop and we can just pattern match on it and say, okay, so is this the recipe that says, you need to keep going, and then we're going to keep going. And if this is the recipe that says that we're done, then we're going to be done, right? And this loop is going to be tail recursive. So we're going to start by creating a new file and creating this class trampoline. And instead of returning thunks over here, we're going to use trampolines. Okay, so the goal, and maybe I should actually start doing it like this. So what we should do? We should start compiling. Okay, so how are we gonna do this? So let's see. Instead of thunks over here, we're gonna say this is going to be a trampoline of super. Come on, super. Like this. Okay, and now what we probably should do is we should probably start implementing trampoline. Yeah, let's start implementing a trampoline. Okay, so let's not save this file. Let's do that. Whoops, that's not what I wanted to do. I pressed down instead of right. So over here we're going to create a new file. Let me save it. The rendering issues. Hold up. There we go. Okay, so let's call it trampoline.scala. Okay, and let's put it in the. I wanted to scroll up. Come on, scroll up. Copy the package. All right, so we're gonna have an object trampoline here. Trampoline. Okay, and we're also gonna import that object over here. We're not saving the files yet, so we're just typing like crazy. Okay, so the idea is that a trampoline is going to wrap the thunks, right? So we're going to have a final case class thunk, right? So this will just abstract over the thunk, okay? So it will need some type, result, and the thunk is going to be called thunk, okay? And it will produce a trampoline of result, okay, like this. Okay, so now it's starting that we're running out of space, huh? All right, so now that we have that, let's see if it compiles. It does not. It says I can't find trampoline. Okay, so trampoline itself is going to be a sealed abstract class trampoline plus result, like that. Okay, let's see if that's enough. All right, so let's try to save this file and see where it all goes wrong. Okay, so the first problem is that it says in line 172, it found a thunk basically, but it wanted a trampoline. Let's go into line 172. Okay, over here it said I found a thunk, but I wanted a trampoline. Well, let's try to create a thunk here, right? So instead of this, we can loop this, and instead of this whole thing, we want to create a trampoline. So a thunk is a trampoline. It is something that we have forgotten. Extends trampoline of result. Okay, like this. Okay, so we're trying to create a thunk here, and what it wants is a function that produces a trampoline. So if we copy that, it's not going to help, right? If you scroll down, if I save, it's going to say missing parameter type. Okay, whatever. As we can try to help it out like this. Oh, sorry. S is a set of super. All right. So now it says, okay, so I found something that takes a set of super and then produces this thunk, but I wanted something that takes nothing, right? Like this as a thung, and produce a trampoline. So the idea is that the thung is not what we need here. What we need here is a different case. So we need a case class done, right? It will also have a result, and it will just have it over here, result. And this is also a version of the trampoline, right? So now over here, instead of producing a thunk, let's just produce a done, right? So all of this stuff is not necessary. All that we need to produce is a done of S. S comes in, then comes out. Okay, so this is a continuation that takes an S and produces a trampoline. Okay, so now, what does it say? Found set of super required super. That means we ruined something over there at the top. All right, so yeah, it's not a trampoline of super, it's a trampoline of set of super. There we go, set of super. All right, what else? Okay, 175. Okay, now this is the part where we're running the loop. Now we could have a function called apply over here that produces the result somehow, but it's common to call it somehow differently. So instead of this, we're just going to call it the result. So instead of doing that, we're just going to say result. Okay. So this function is going to be our tail recursive function. It's just going to take the trampoline and it's going to say, okay, so if we're already done, then just return the result. Otherwise, if we're not done yet, if it's a thunk, run the thunk, and then run the result. So because the result is in the tail position, this is going to be a tail recursive function. Call annotation tail rec. There we go. All right, it says not found, blah, blah, blah. It means an import is missing. Import trampoline. All right, so 175. Oh, I didn't save the file. Okay, there we go. And also we can remove this. All right, so everything compiles now, and maybe the tests are also running, actually. I'm not sure. Yeah, the tests are also running. Let's switch back to compile. Okay, we have a problem now that things like annotations are not super helpful anymore. And things like type Tetris are also not super helpful anymore. Because what we need to do here is exactly that part that the trampolines are really good at. The trampolines are good at saying, okay, so you have an algorithm, just show me the places that are supposed to be in the tail call position. And then I'm going to make sure that they actually are in the tail call position. Okay, so it happens that we need over here, we need to put this continuation, because this is exactly that thing that was causing us stack overflows. We need to actually wrap them in this thunk, right? So over here, we need to say that this thing, this entire thing, I'm going to put parentheses around it. I'm going to say that this is a thunk that take that, produces that. Okay, same thing over here at the bottom. Parentheses. There we go. Still compiles. The test is still green. Now let's switch to running and let's see if it actually solved our problem. Why me? Why me currently runs just high. Let's do that. All right, so this should solve our problem, but this should run a bit longer than these few. So before it was running like for 10 seconds or so, and then it exploded. So while it's running, first of all, let me explain to you why this whole thing is called a trampoline. Why such a weird name? Now the name is coming from the fact that every time we call a result, it decides if it's done or if it's a thunk. And if it is a thunk, then it goes into this computation that was in our set right over here, and it goes over here, and it calls it evaluates this thunk, right? So it just runs this function over here, right? So it goes in there, it builds up the stack that it needs to run this continuation, then it pops everything again from the stack and returns control to result. And then the result takes the next instruction and says, okay, so are we still a thunk? Yes. Then it goes back in, jumps in the computation, builds the stack, goes down, goes back to the result. right? It goes up and down, up and down, up and down, as if you were on a trampoline. And that's why it's called Trampoline. While it's still compiling, it's not compiled, it's actually running. While it's still running, by the way, it already runs longer than 10 seconds, which means at least it runs better, quote unquote, than before, because at least by now the previous version already exploded. So while it's running, we're gonna improve the trampolines a little bit by introducing a few helper methods. So over here we're gonna have a helper. I'm gonna have it like this. A helper that is going to produce the done case. So it's going to be just a function that takes the result, R result, produces a trampoline result, right? And it's basically just a factory method for done. And the other one is going to be the tail call, and the tail call is going to use the thunk, but this time as a by name parameter. By name parameter, right here, like this, equals thunk of. It's going to just wrap it into the thunk function, like this, right? So now that we have these two, we can actually make both of these private like this, okay? Because on the outside we're just going to be using the done and the tail call helpers. So I'm going to press enter over here because when it finishes running, I don't want it to run again, because I want to start saving this file, and I want to go back here. And now over here, instead of capital done, I can use this small done, and because now this function has exactly the same signature, I can just say done over here. Instead of this, I can say done. Okay, and over here, instead of capital thunk, I'm going to use tail call. And now I don't have to do these things because now it's a by name parameter, right? So basically now you're just going to your algorithm, whatever it is, and you're marking the spots that are supposed to be tail called, and you're just starting the whole thing with done, right? And the done is basically the same thing as this and continuation, right? So I'm going to save that file, and by now I actually don't have anything more to say. So I'm just going to cut out the part where it runs the algorithm until it finishes, and we're going to continue from there. So what we see is that trampolines are a teeny bit slower. Already you see this. In fact, in the next video we're going to see that the trampolines can actually be much slower. We're going to get there. So what I've forgotten is that we also have the other version, right? The other version. In fact, you know what? Because now this thing is so explicit, let's just inline that so we can have this, right? We don't have to be so explicit. Okay. So like this. Let's go back to running the tests. All right. So I just want to keep the while version also up to date. So let's go to the while version, and over here we're going to say trampoline dot result, and this is going to be our trampoline like this, and this is going to be the same. And we're going to go back to the top, and I'm going to say over here, this is not a thunk, this is a trampoline of set of super. The whole thing is just done, and we're going to go back here, and I'm going to say that this is a tail call, and this is a tail call, close the parentheses, and we should be done. All right, what's up here? Continuation of, yeah, I forgot to remove that. There we go. All right, everything is still green. All right, so now that we have trampolines, maybe we can go back to Fibonacci and do the same thing. So for the Fibonacci, we're gonna find a version that is trampoline with CPS. It's probably this one. Yeah, like this is the one that is the one that we want. Yeah, this is the one. So we're gonna copy that. We're gonna paste it down over here. Fibonacci CPS trampoline like this. Okay, so let's set it down there as well over here. Yeah, so we have CPS. We have CPS trampoline. Are we running that? No, we're not running that. So let's inline that. Sorry, uncomment that. Let's let's go back to here. Okay, there we go. All right, so let me press enter and let's start running Fibonacci's again. Sorry, Homegrown collections, Fibonacci. All right, so the last one, I just jumped down, this one, Fibonacci CPS Trampoline. So we want to convert it. So we're going to jump straight through the thunk. So we're not going to convert this continuation first to a continuation that produces a thunk. We're going to go straight to trampolines. So first of all, at the top, let me import trampolines. Import trampoline. Like this. All right, let's go back to line, I think it was 120. Yeah, so it was over here. So what we want to have here is not long to long, we want to have long to trampoline of long. Trampoline of long, goddammit. All right, trampoline, and we're going to start, instead of identity, we're going to start with a done. And we're going to have a result over here. And now all we need to do is we need to find the continuation over here, put into a tail call. And this one, remember, this is the one that was not in the tail call position. Tail position, tail call. Let's put it like this. Like that. And close it like this. Okay. Obviously something's wrong. Value result is not a member of long. Oh, okay. This should also be a trampoline of long. There we go. Okay, still exactly the same values. We're still printing out like is odd and is even. Maybe we should not do that. Is odd. There we go. So let's comment out these two. All right. Okay. All right. So now we have a Fibonacci version with CPS and it is trampolined. And you know, we're using trampolines to get rid of tail recursion. So I would like to show it to you that you know, I would like to give it like a really big number and then show it to you. Oh, okay, see, like without the trampolines, it actually throws an exception because it's a Stack Overflow, and with the trampolines, it doesn't. The problem is that what trampolines are good at is not at optimizing the algorithm. What they're good at is eliminating tail calls, which is why some people get like really angry when people say tail call optimization instead of tail call elimination, because nothing is optimized. It's just that the tail calls are gone. So what we're going to do instead, because you know, if I run Fibonacci of 40, it's going to take around 8 seconds to run. But if I run Fibonacci of 50, it's going to run around in like 9 minutes or so. And obviously we're not going to do that because Fibonacci, you know, the originally, not the original Fibonacci version, but the original tail recursive version of Fibonacci. In fact, let's go there. It is this one. I mean, sure, it's tail recursive. Sure, it eliminates the tail calls, but also at the same time, which is why it's actually really wonderful, it uses a technique called memoization, and it remembers all of these results. So at the point where you need those results of the two previous elements in the sequence, you already have them, so you don't have to repeat those needless recalculations and to build this like really nasty tree. So what we're going to do instead is we're going to jump to Factorial, and we're going to play around with Factorial a little bit. So let's see how we're going to do this. So first of all, let's go down and to find and find the Phoebes. So instead of Phoebes, we're going to have Facties. I don't know why. Okay, we have Facties, and it's going to be a sequence of Factorial that we don't have yet. So let's just add, and let's switch to Facties over here. Facties. All right, so let's go to Factorial over here. Let's create it. Define Factorial, long. This is the traditional naive version, right? If it's 0, then it's 1. Otherwise, it's n times Factorial of n minus 1. Okay, so now it should run only once. Yeah, so this is Factorial 1, 1, 6, 24, 120, 720. Yes, I recognize it. Okay, so what we're going to do now is we're going to, as always, we're going to pretend like there's no tail recursive version out of it. So we're gonna jump straight to the version with CPS and trampolines. Okay, so we're going to have Factorial CPS trampolined. Okay, and it's going to take long. It's going to produce long. Okay, like this. So let's add it over here like this. Okay, so as always, we're going to start with a loop, and at the bottom we're going to call the loop with n done result, same as always basically, right? So this loop is going to take an x and a continuation from a long to a trampoline of long, very similar to Fibonacci. Produce a trampoline of long, basically the same thing. That's exactly where we're taking it because it's so similar, but it doesn't have to build this nested tree. Continuation of 1 or continuation of 1. Otherwise, it's just going to run the loop. Okay, the x is going to become x minus 1, and whoops, I did not want that. Okay, and continuation is going to become this, and we're going to mark the tail call with a continuation of x times ACC, like this. Okay, let's see if I can spell. Yeah, I can. All right. So before that, actually, let's create another version, the one without trampolines. Okay, so we're just gonna have a long over here. I'm gonna do the tail call. Just gonna do the identity over here. Return it right away. Let's not do trampoline. Okay, so we have the Factorial CPS. Let's see if it compiles. I didn't edit there yet. Okay, so let's have it over here. Factorial CPS. All right. So what I want to do now. Okay, so obviously it runs and it still works. So what I want to do now is I want to comment out these. Right. So I want to run only the Factorial CPS, and I'm going to give it a big number. So okay, so instead of that, we're just going to run from 9999 to 9999, like this, right? So only once. Let's see what's going to happen. Stack Overflow. All right, and what we can do now is we can switch to the where is it? So comment out this one, enable this one. This is the one with the trampolines, and now it should be fine. Now the result is 0, not because of trampolines, it's just because of the regular overflows, right? We've seen that the trampoline version also works, right? So if we run again from 0 to, I don't know, 20, right, it produces valid results. It's just at some point it overflows. The same thing would happen to the regular tail recursive version of Factorial. All right, so what do we got so far? It turns out that we can take any algorithm and we can transform it into a CPS version of it. Then we can take the CPS version of it and we can transform it into a version that produces thunks instead of the results right away. And then we can take that and transform it to a version that instead of producing thunks, it produces trampolines. And we can walk through the trampoline ourselves in a tail recursive way, and therefore we don't have problems with tail recursion. Now the question is, if all of these steps are mechanical, why can't we skip them? Can we skip them and just go straight to trampolines? And the answer is yes. There's a teeny part that is missing that we're going to do in the next video. But it turns out that we can already see the benefits. And we're going to see the benefits with mutual recursion. So this thing over here, remember, this is even and is odd. Look at it. It doesn't have any continuations, and it doesn't have any thunks, and doesn't have any trampolines yet. But it turns out that we can use trampolines right there without going through continuations, without going through thunks, anything like this. So let me revert a few things. Let's do that. Let's not write this. Let's not run this. There we go. Let me scroll down a little bit. All right, so we have this is even and is odd, which is a very, very traditional example for trampolines. And what you can do is you can say, okay, so let's not run this. Let's run that. In fact, first of all, let me demonstrate a tail call. Let's just print out is odd of 99999, right? So this is basically 100K. Let's see. All right, Stack Overflow. Okay, so it turns out that what we can do is we can go over here and we can say that this is going to be a trampoline of Boolean. Right, and then we can say that this thing is done, this thing is a tail call, and we can do the same thing at the bottom. Done, tail call, like this. And now all we need to do over here is to produce a result. And all of a sudden, of course it's odd. Right, let's do the other ones just for fun. So we have the is odd. Let's do the is even. right? And yeah, let's do this again with 100K. I don't know why I'm doing this. Like sometimes I'm sitting at this and I'm looking at this and it just makes sense to run it again. Is even. Is it 10K? Hold up. Okay. There we go. All right. Cool. So again, in the next video, we're going to see how we actually can do this straightforward jump, right? So through the continuations with Stack, we can go from any algorithm straight to trampolines. So far, one tiny part is missing. What you can do is you can try and implement a version of Factorial, for example, or Fibonacci. Fibonacci is going to be a little bit more complicated with trampolines and see how far you can get. Yeah, that's all. So so far we're pretty much done. So I'm just going to commit everything as is. Git status, right? Not forget to add the trampoline. All right, git commit -am, and that's gonna be video 16 trampoline part 1. There we go. That's an equal sign. I want a hyphen. Video 16 trampoline part 1. There we go. Let's push it. And that's all I got for you today. It's been Vlad, devinsider.com. Like this video if you did, subscribe if you want to improve the developer inside you, and most importantly, take care.